Hello and welcome to 28th lecture in 19th chapter of our comprehensive course on AI, ML and DS. The name of this chapter is A Comprehensive Introduction to Statistics. And you can see that we have done a lot of total, this is 28th lecture. So you can understand that perhaps no other chapter has so far has been dealt with in so much detail. We were doing various statistical tests for hypothesis testing, and among them, one of the tests was t-test. Another was in t-test there are single t-test, then paired t-test, then double t-test, and then maybe that is double is not called double, but independent t-test, IND, independent sample t-test. Then there is that ANOVA, then there is chi-square test, and all those. Now we are doing this correlation test. We have already done a little bit of discussion here and there about this correlation test. So we know we have plotted this kind of diagram also, which is called heat map, which we get from the correlation matrix, right? So that is about that we want to do a little bit more discussion. So first, what are some practical examples? So in machine learning, if we want to evaluate whether the number of hours spent on studying is positively correlated with exam scores or not. Positively correlated means as you spend more hours for studying, your exam score keeps on increasing or not. Okay. Now again, null hypothesis will say that number of hours spent for studying has no correlation with exams score, so no correlation exists. But alternative hypothesis says that there is a positive correlation. So that means as you spend more hours, your score will also improve. Okay. Similarly, second example from a business case, that was machine learning or education domain, testing if the ad spending is correlated with the revenue or not. So again, that means suppose on y-axis I plot my revenue and on x-axis the amount which I spend for marketing. Then the question is that as I go on spending more and more money on advertising, does my revenue goes on increasing positively? That means as ad revenue increases, then as ad budget increases, my sales or the revenue also increases or maybe decreases. But in short, there is some definite correlation, right? Again, null hypothesis will say that the revenue and the ad spending, they are not at all correlated. There is no correlation. But alternative hypothesis will say that they are positively correlated. When I say positively correlated, that means that as you spend more money on advertising, revenue increases. That is what alternative hypothesis will tell, right? And a retail company wants to test if the number of ad runs is correlated with monthly sales. Okay, so here my null hypothesis says that no correlation between the number of ad runs. So ad run means on TV the advertising is very costly, so companies have to budget this, that in one day how many times the ad of one particular product will run. Maybe 3 times, then you have to spend some certain money, but instead of that 5 times, then you will have to spend more money, right? So and 10 times, then you will have to spend more money. Now the question is, as I run my ad for more number of times, will that positively correlate with my monthly sale? Then answer again, null hypothesis will say that there is no correlation between the monthly sale. And here alternative I forgot, but alternative hypothesis will say that a correlation does exist. So that means here it would be like this, that number of ad runs and revenue or and sales are positively correlated. So positively correlated means that as I run my ad more number of times during the day, then my monthly sale will also increase. That is what alternative hypothesis says. Null hypothesis says that there is no correlation between this variable at number of ads run and monthly sale. Now in all examples you can see one thing, that mostly correlation test, not mostly but always, correlation test is only applied for numerical variables. All are just numbers, number of hours spent, exam score, so these are both numbers. Then ad spending and revenue, again both numbers. Then number of times the ad is run and monthly sales, all are just numbers. So remember that just like chi-square test is applicable only for categorical variables, similarly correlation test is only applicable for numerical variable. Okay, so if you do these two tests, correlation and chi-square, or maybe ANOVA also if you want to be further sure, then you have fairly covered both categorical and numerical variables in the data analysis, right? So let us take one example for the second case, that is if ad spending is positively correlated with revenue or not, right? So for that we generate a synthetic data, monthly sales and ad run. So actually it is not example for code example for 2 but 3, right? So that means number of ad runs is positively correlated with monthly sales. So we generate a synthetic data for that. Now obviously up to this you should not worry at all, because this data you will not have to generate. Your client will give you this data and he will ask you this question, that if I run my ad instead of 5 times a day on the TV, if I run my ad 10 times a day, then will my monthly sale also increase proportionately, or maybe at least it will increase positive correlation? Does it exist or not? So null hypothesis will say there is no positive correlation, and alternative hypothesis says that there is positive correlation. So you have just created the data. Here all are again usual libraries, NumPy, Pandas, and Matplotlib. This is one library from scipy.stats. In this part, inferential statistic, we are using various features of scipy.stats only. Import Pearson R. So Pearson correlation. R stands for relation or correlation, right? Now there is one thing that here this step is still not used at all, because here we have just created the data. So NumPy is used and Pandas is used. We have not plotted anything, so even Matplotlib is not used, and we have not found correlation, so this is also not used. So this is my data frame. It says that these are the values of ads run per day, say 11 times, 8 times, 17 times, and so on. Maybe this was some IPL day or some important football World Cup final day. So on that day you had run the ad large number of times, and these are the corresponding monthly sales. So this is ads run per day, average mean value over 30 days, right? And this is monthly sales. So if you do this kind of sample is given to you, and you are asked that question, that does this two variable have some positive correlation? So it is very easy to do that. First you can decide visually, and visually you can plot a scatter plot, and if there is a positive correlation, then you will see some this kind of thing, right? This kind of thing. So on this axis you will see that this is the number of ad runs, and on y-axis it is the monthly sales. And if you see this kind of trend, that means as the ad runs increase, the sales also increases. Okay, so let us try to plot a scatter plot, and you see that it is that kind of trend only. You can roughly pass a line like this. So as number of ad runs increases, monthly sale increases. But again I said that visually or anything you should not give. You can never give that kind of answer to your boss, that see this I have plotted scatter plot and it shows. You can say that this shows that there is a likelihood that this number of ads run and these are correlated, but I will conduct my Pearson correlation test. So now this step that is this library is used, that from scipy.stats import Pearson R. Now that Pearson R is used here. Again Pearson R is also a test like t-test, etc., where as an output you get two parameters, just like in other the parameters were t statistics and p value, and or f statistics and p value. Similarly in this the two parameters are correlation and the p value, right? So that it will give me how much is the correlation between this variable and this variable, and then that is the what is the p value of that correlation, because having correlation is not enough. Does that correlation border into the limit of statistical significance? So is the p value greater than alpha 0.05, so that you can nullify this null hypothesis which says that there is no correlation, and you can accept the alternative hypothesis like that. Okay, so for that you can use this Pearson test. So read from right to left. So Pearson R test takes two arguments. First argument is from your data the independent variable, that is ads run, and second argument, that is x here, number of ads run, and then the other argument is the independent variable or something which you want to predict. So that is the monthly sales or y variable. Okay, so it is very easy. Pearson R x y, that is how it is remembered. Okay, now if I find it and find this p value, then and if my p value comes out to be less than alpha, then I will say that reject the null hypothesis. But if p value is found to be greater than alpha, then I will say that I fail to reject null hypothesis, right? So let us calculate p value, and this is my synthetic data, and data.head is this first 5 rows. Okay, and this I think now there is no need, because I have printed entire data frame only. So maybe this is not required. Why unnecessarily crowd our output, right? So just Pearson correlation coefficient, and that is coming out to be 0.85919, or you can say that monthly sales and ads run, they have 85% positive correlation. 85% positive correlation. So that means that is pretty high correlation. And if this is negative, then in that case you would get this kind of graph. So as more ads are run, sales decreases, this kind of graph. But here you are getting this kind of graph. The trend line is like this. So that is called positive correlation. So plus 0.8519, high positive correlation. And the p value is 0. Again 0, because here formatting is done so that only 4 digits are left. Otherwise, if I do it this way, then you can see that there is some 0.00080, then 236. That much p value is there, right? But that value is in short very, very less. Or that means this part is obeyed. P value is less than alpha. That part is obeyed, and therefore I will say reject the null hypothesis. There is significant correlation between ads and monthly sales. So null hypothesis was saying that there is no correlation, but now I say reject it. However, remember one thing about this hypothesis testing. You just reject the null hypothesis which says no correlation. So that means you get that yes, there is a correlation. Now that correlation can be positive also and negative also. I said that you might get a graph like these also, x versus y graph. And alternatively, you might get X versus Y graph this way also. One graph is this, as X increases, Y also increases. So as more ads are run, sales increases. But you might get this way also. That is, as X increases, Y decreases. So your p-value just says that neglect null hypothesis or invalidate null hypothesis, reject null hypothesis, and that means the p-value says that there is correlation. But how much, which type of correlation it is, whether it is of this type or whether it is of this type, that idea p-value cannot give, right? So that idea is given by Pearson correlation coefficient. That idea here, correlation coefficient is positive, so I would say that this kind of correlation is not there. It is always this kind of correlation. As X increases, Y also increases, right? So that is what it is. Another thing is that same idea I can get visually also by plotting scatter plot. So that will clearly show the trend that as X increases, Y increases. That is what these data points show. May not be perfectly linear, but there is a positive correlation, right? So this is that discussion. Explanation of code, there is nothing much to explain in that, and the interpretation of result, there also there is nothing much. Now, however, some extra point I want to discuss, and you should be very careful about saying. Suppose you get here, instead of here you got p much small, and therefore you said that reject null hypothesis. But suppose you get, say, p is equal to, just as an example I'm saying, suppose you get p equals 0.2. Now that 0.2, which is greater than 0.05 significant value. So if p is greater than alpha, then you will enter this else part. You will fail to reject null hypothesis, or that means that you will have to say that null hypothesis is valid, and that means no correlation exists between ads and sales. Now does that mean there is actually no correlation between ads and sales? Then no. Pearson correlation has one big limitation, that it can only measure linear correlation. No linear correlation exists. If I get this kind of P, then I should not speak that no correlation exists between the ad runs and the monthly sale. Instead, I should say no linear correlation exists between the ad runs and the monthly sales. Okay, so what I am saying is that a non-linear correlation may still exist, and Pearson correlation coefficient does not give any idea about that, right? So that is one thing I want to say. What I am saying is something like this. So what I am saying is something this way, that if you get p greater than 0.05, that is p value greater than alpha, you should not write this statement that fail to reject null hypothesis. That much is fine, fail to reject null hypothesis, and therefore no significant correlation between ads run and monthly sales. No significant linear correlation between ads run and monthly sale, because it is possible that the two variable on the x-axis I am using on the x-axis I am using that number of ads run, x variable, and on y-axis my monthly sale is there. Then it is possible that y and x are related by one this kind of equation, y is equal to x square or 5x square or that kind of equation, so that it is a parabolic relationship, not linear relationship, right? So in that case, it is clear that Pearson correlation will still give a high p-value, and you might be misled into that oh, so then there is no point in running more ads because it is not correlated with my monthly sale. In fact, it is very sharply correlated with number of ads. Your monthly sale increases as the square of number of ads run. So instead of 2 ads, if you run 4 ads, then sales will become, so that is ads if you do 2 times, then sales will become 4 times. Instead of 1 ad, if you run 3 ads, that is if number of ads become 3 times, then sales will become 9 times. But that kind of non-linear correlation, Pearson correlation test does not capture. It is only for linear correlation, right? So there have been many other correlation coefficients defined, like some is called Chatterjee correlation coefficient and all others, but we don't want to go into it. So please remember that no significant linear correlation exists between, and here also you can write that here I got p value much less, so that means p is much less than alpha. So there is a significant linear correlation between ads run and monthly sales. So that is what is important about this kind of graph, this type of correlation, Pearson correlation. So it not only gives whether or not there is correlation by p-value, it tells whether the correlation is positive or negative by correlation coefficient or by scatter plot, okay? And it also says whether it is a linear or non-linear. So if it is a linear correlation, then in next steps of machine learning, you have to build a model for which you can select linear regression algorithm or other linear models, and there is no need of trying non-linear models. Okay, fine. But here a case I got that p is much less than alpha, and p is much less than alpha means reject the null hypothesis. So there exists a significant linear correlation between ads run and monthly sales. So that means there is no need of trying non-linear algorithms like SVM or so on. So just a simple linear regression is enough. Okay, so that is point number 1. Point number 2 is that this was a simple case in which my y, that is this monthly cell, that depends on only one way factor, ads run, right? So that is why just a correlation printing is enough. But what if I have a data frame and in which suppose this is the my dependent variable yield, okay, crop yield, and these are various feature variable. Now this Julian day is fine, that you can avoid also, but others time since sown. So how much yield will occur? Then that does it depend upon the time since the seeds were sown, time since last harvest was taken, total radiation, okay, then total rainfall, average air temperature during the process when the seeds were sown to the harvest, the day when harvest was taken, average minimum temperature, maximum temperature, average soil moisture, day length, so that and percentage coverage. Now that means maybe percentage irrigation coverage, or maybe you how much in how much whether you saw you had sown your seeds very densely close to each other or far away from each other. I don't know what is that percentage coverage, but in short, these are my x variable, x1, x2, x3, and so on up to xn, and this is my y variable, right? And I want to decide if I can fit a linear model y is equal to beta 0 plus beta 1 into x1 plus beta 2 into x2 plus beta 3 into x3 plus beta 4 into x4 plus beta 5 into x5 plus beta 6 into x6 plus beta 7 into x7 and so on up to beta 9 into x9. Suppose this Julian day, I just remove it. Okay, so in that case, I want to find a linear model which can help me predict how much will be the crop yield provided these parameters are given to me. These 9 parameters or whatever, 10 number, whatever number I have not counted, but these parameters or features are given to me. Now, for that, I find such correlation, Pearson correlation, and I plot this kind of heat map. We have already done this thing in some earlier examples, so you are knowing that. And suppose this kind of heat map is obtained. So wherever there is high correlation, we can remove those two, one of those two variables. For example, time since last harvest and this that is total radiation, right? That is 0.83% correlation. So maybe you can remove time since last harvest and keep the total radiation, or maybe you can remove total radiation and time since last harvest is kept, because if you keep one of the two, still 83% of the information is retained. That is the rough meaning of correlation, rough meaning, however. Okay. Similarly, average temperature and this average minimum temperature and average maximum temperature and average air temperature, they are having 99 and 98 correlation. So there is no need of taking minimum and maximum also. Just taking average air temperature is sufficient, because they give more or less the same information, right? Similarly, here negative correlation but 0.97, that is between what? Julian day and day length, right? So you can keep maybe Julian day you can remove, and the day length you can keep as one variable. So wherever there is high positive or high negative variable between two features, remember this is my response variable, what will be the yield? That is what I am trying to predict. If I magnify slightly, then this yield is what I am trying to predict. But if two features are closely correlated, then in that case I can say that I can keep only one of the two features. So if you do that way, then here in this case you can see that many of the variables can be removed. Many of the feature variables can be removed, or many independent variables can be removed. And from maybe 10 independent variables, you can reduce it to a model which depends on only 6 independent variables. So that means y is equal to beta 0, beta plus beta 1 x1 plus beta 2 x2 and so on up to beta 6 x6. And related features are removed, only one of them is kept. What is the advantage of doing that? We have discussed that. So it gives an idea, it gives a simpler model. And what is the advantage? It reduces overfitting. What is overfitting? Overfitting means on your train set, the data, the model will give a very accurate result, but on test set, it will give very poor result. Okay, so that means on seen data, because model is trained using the train set, so on the data points which it has already seen, it will give high accuracy, but on unseen data, test set, your model was not trained using the test set, right? So then on unseen data, it will give very poor accuracy. So then that phenomena is called overfitting. But real test of a machine learning model is that only, that what it does on unseen data, right? So then overfitting has to be avoided. And the way to avoid overfitting is avoid complex model. Complex model means where the y, your response variable, depends on so many of different features, that would become very complex model. So avoid that. And you can see that Pearson correlation coefficient for this is coefficient between each pair, that you should understand. Okay, so that is why this kind of heat map or square like thing is given. So this is correlation between what? Julian day, and here down you go, then it is the time since last harvest, right? Similarly, this 99 is correlation between what? Average air temperature, and down if you go, average minimum temperature. 98 is correlation between average air temperature and average maximum temperature, right? This so you can avoid that kind of highly correlated feature and keep only one feature to make your model simple and avoid overfitting. This is the real and the most important use case of Pearson correlation coefficient, right? Okay, and this we will be doing in practically every data science problem. There will not be any data science problem which will not do these things, except of course there are NLP and maybe then time series and all that. They are totally different things, but usual classical data science problems, they will always need you to this. do this. Now, one other important feature of this type of heat map is that I told you that if these are features, okay, these feature variables, I'm forgetting about this yield. That is my response variable, which I am trying to predict. But these are my feature variables, right? And from which I will find highly correlated like this dark brown or etc. because that is what this scale says, or highly negatively correlated, maybe like this, like dark blue. That is Julian day and day length. They are highly negatively correlated. So maybe I can just remove any one of them. Okay, but I can also get some idea about which features are affecting my response variable. So for that, I will see the correlation between yield and all others. So that is here this bottom row. So yield and time since on, they have around 0.20 correlation. Then yield and this time since last harvest, very poor correlation. So this my yield is, you can say, practically does not depend on this 0.06. And then yield and this time total radiation, that is 19%, 20%. So both this 20% and this is also around 20%. I will keep it. Okay. So that means yield depends on this. Yield depends on this. Yield also depends on total rainfall, but the yield does not depend on time since this last harvest. Similarly, this is also very poor correlation between yield and this average air temperature. So maybe just like I removed minimum and maximum air temperature and kept only average air temperature, because minimum, maximum, and average all were giving the same information due to their high correlation. But now when I see the correlation between the response variable and the average air temperature, then I see that there is so poor correlation, 0.6, 0.06, that I don't need to even keep that average air temperature. So that means average air temperature has almost no effect on the harvest. Okay, of course that is not considering that global warming. Otherwise, some 6% effect is there. Then average minimum temperature, that has 7% effect. So maybe okay, one of these two you can keep. Then average maximum temperature has practically no effect, 0.02, only 2%. So you can remove these three if you want and make a simple model that yield is a function of this, that is time since zone, this 0.19, that is time total radiation, this total rainfall. Avoid these three, directly come to this 0.21. So average soil moisture, then highly correlated with day length. Yield is highly correlated with day length. So maybe the crop which was sown was for summer, and therefore it is highly correlated with day length. And this is 30% correlation with the percent cover. And okay, so I can not only decide which two feature variables are capturing more or less equal information, and therefore I can remove, say, out of these three I can keep only one for reducing overfitting, but I can even get a rough idea that my y should be a model of y is equal to beta 0 plus beta 1 into time since this zone, and z beta 1 which should be negative because this correlation is negative, plus beta 2 into this total radiation, and that beta 2 would be positive, plus beta 3 into total rainfall, and beta 3 also should come out to be positive. Then beta 4 into this thing, that is the average soil, and beta 5 into this thing day length, and beta 6 into this thing, that is percent cover, right? Okay, so I can roughly get a model that my yield depends on these factors which are having, say, more than 20% or 18% correlation. However, that means I can start building my model by taking these factors. That would be a good beginning. That type of model which we build by using only Pearson correlation is sometimes called the Bayes model. Bayes model means at least minimal accuracy of any other model. You may use many sophisticated algorithms like random forest and XGBoost, but its minimal accuracy should be equal to this Bayes model, right? But there is one big if in that also. Just like one problem with Pearson, I said that it does not measure non-linear correlation. Similarly, one more problem is that here you are just assuming that your this yield variable is, just because it is highly correlated with this feature, so you are assuming that correlation is the causation. So that means that this time since zone, that negatively affects the yield because it is negative correlation, and this positively affects the yield, and this positively affects the yield, and so on. But correlation is actually not causation. So that may serve as a good beginning for forming a Bayes model, but the real model, just like actual, that is just like that kind of rough idea which a visualization gives, this kind. But the final conclusion we always do by exact p-value. Okay, similarly here also, exactly you have to build the model using those features, and then you have to find its accuracy. If it gives sufficiently high accuracy or other parameter F1 score, etc., then in that case you may say that yes, this correlation appears to be causation also. Now, what is the meaning of this word correlation is not causation? So for that, there is this important website called Spurious Correlations. So sorry, I deleted the cell. Okay, I should have clicked it, right? So Spurious Correlation, and internet is closed. Why? What is the problem? So this is that Spurious Correlation website, right? Yeah, here it is. So maybe something wrong occurred, that's why. So anyway, so this is that website. Now you will find that sometimes completely irrelevant two variables can find perfect correlation, but that does not mean that one is the cause of other. For example, number of movies Elijah Wood, which is some kind of actor, correlates with number of orderlies in Oklahoma. Now, is there any relation between this? How many movies a particular actor will occur and how many orderlies exist in Oklahoma? Then no correlation. Air pollution in San Diego is directly, perfectly correlates with the popularity of first name correct. So, do you hold all the people whose name is this that you are responsible for the air pollution in San Diego? No, because that is just by chance, just an accident that these two are matching with each other. Petroleum consumption in Azerbaijan and number of farm equipment mechanics in Alabama. Now, this Azerbaijan is a country near Russia, and this is farm equipment in Alabama is a state in United States. They are polar opposites geographically on the earth, but somehow you can see that a very nice correlation occurs. One other very strange is this master degree awarded in education and Google search for Ganganam style. This Ganganam style was one dance video from India which became very popular on YouTube, right? And it is seen that how many Google search occurs from the Ganganam site over 2012, 13, 14, etc. If you plot a graph, then that is red, and how many master degrees were awarded in the education, that you can plot by black, then somehow they strangely fit each other almost perfectly. Now, does that mean that that the Ganganam style dance is somehow related with education? No. Or that is the cause of more master degree being awarded? No. So similarly, all these things that GMO using cotton in Texas, genetically modified seeds, correlates with pyrotechnics globally. Now, obviously, again, there is no correlation, right? And maybe distance between Neptune and Uranus correlates with the stock price of Cognizant Technology Solutions stock. And you can see that Neptune and Uranus, they vary this way. Distance between them decreases, increases that way. But then, does it affect the stock price of your a technological firm? Maybe if you are believer in astrology, then perhaps it affects. But otherwise, well, there is no correlation between this. So this is an interesting site, and please go through this site. I don't know why that link did not work. I'm trying again. Okay. Oh yes, I think I tested it 2 times. That is why perhaps. Okay. So let me spurious correlation only once. Go through this website. It is really interesting, and it will permanently print that idea in your mind that correlation is not causation, right? So I told you two limitations about your this Pearson correlation test. Okay, let me this time check. It should open. Yes, it is opening now. Fine. So this is the thing. Now we will meet in the next chapter and see you in the next lecture rather for this Z test, right? Okay. I found that spurious correlation thing from ChatGPT. Then when I asked that, can you suggest a terminology for this sentence, correlation is not causation, then it suggested that it is called spurious correlation, and there is a site also named this. Okay, so that is how I got it. Okay, now this Z test. So that we will do in the next lecture. Thank you.